Okay, it's a pleasure to introduce the last lecturer of our summer school.
Yay!
It's Daniele Oriti, from now delocalized between Madrid and Munich, but officially at the Universidad Complutense de Madrid. And he's like the most quantum gravity person we have here. So I asked him to go very, very gently for this quantum information audience. So looking very much forward to your talk.
Thank you. Can you hear me? Can you hear me?
Is it on?
Should be.
Yeah. This is mic 2, mic 3. 3.
Shall I try? Oh, now it does. Good. Better now? Is it better now? Can you hear me? Yeah? Do like this? Yeah? More? No? More convincingly? Okay. So, I approach these lectures with the peace of mind of somebody who has been given an impossible task. And so I don't believe that anybody can be confident I will introduce or explain quantum gravity in 3 lectures. That is regardless of whether I leave time for questions or not. One main reason is that there's no quantum gravity. I mean, it's not that we have it here. There are many approaches, many different perspectives, many different ideas. And this is probably a simplified picture of the landscape, and probably also a biased one from my own perspective. There is a variety of approaches, formalism, many different issues. But in fact, there are also mutual relations and many shared issues, and I would argue that we share the same goals. So this is a recent picture of a quantum gravity conference. That's how people work and interact. They're very, rationally and friendly, but seriously. So there are several sub-communities, and in some longer version of the lecture, I would identify different figures within the community, those still looking for jobs, those that form the majority of the community, those interested in formal mathematical tools, they are the ones pointing at the sky. Then there are the ones who are actually looking towards the Earth for phenomenology and observational constraints and so on. An even more realistic picture is given by... I'm not sure what you're laughing at. So there could be even tension between different communities. Every discussion is settled by purely rational tools and good manners. But indeed, the quantum gravity issues and goals are, for the most part, shared. And even when you look at the details of different formalism, there are many shared mathematical structures, ideas, and even some common shared results. So the focus of this series of 3 lectures will not be to present a specific approach, but to focus on this broader perspective. It remains a rather odd lecture compared to the earlier ones you had, because first of all, I don't have the luxury, as I said, of just working within a given framework. I cannot just take, this is the theory, now I'll tell you why it's interesting and what is puzzling about it, or what are recent cool results or progress. I cannot do that. And moreover, I had to stay, because I want to cover many different ideas and issues, I have to stay at a rather superficial level. I apologize. You can trust me that at least on a part of the material, I could go into all details. On other things, if it's not directly something I worked on, yeah, my own understanding is, if not really superficial, is medium to superficial. But you're welcome to ask, and I will try to be honest in telling you what I know and what I don't. So the goal here will be just to outline the general issues in quantum gravity, the choices that have to be made when you want to approach the subject and you want to work on constructing a theory. What are the different perspectives, and I'll try to really outline different possibilities rather than specific results. When I mention results, it's because they are examples of a particular possibility, okay, that can be realized by a theory of quantum gravity. And I will focus mostly on conceptual aspects, so that you have a good introduction, I hope, to the problem. You get excited about it, you decide to help, and then you find the theory for us, okay, with time. And the other goal is to show you that there is, to hint that there is an overlap with the issues in quantum foundations, and more generally that the problem of quantum gravity is as foundational as it gets. Okay, so first things first, what do we know already about space-time? In Newtonian physics, space-time is modeled and therefore understood as having a continuum nature. We assume, and it seems to work at the Newtonian level, that there is a preferred foliation, meaning there is a clear notion, a clear distinction, and a clear meaning for space and a time direction. Okay. Any type of invariance you have that keeps the physics the same across different observers or different ways of describing space and time and motion will be Galilean relativity, so Galilean invariance, which is the type of transformation, mathematically speaking, that preserves this structure. This preferred temporal direction and preferred foliation are absolute structures in GR. There's nothing dynamical about them. You could say they're not really physical because they do influence how particles and objects move, but they're not influenced by them. Foliation stays where it is, space stays where it is, time stays where it is, regardless of what dynamical entities, particles and fields and you and me do. From this point of view, in special relativity, not much changes. So from the point of view of space and time and quantum gravity, going to a special relativistic setting is no big deal. Because what changes, of course, is that what is absolute is space-time, is the conjunction of space and temporal direction, and you have to use this conjunction because you can trade, depending on the observer, space distances to time distances and vice versa. There is an interplay between the two. There's no preferred foliation. But there is a preferred set of foliations because there is a preferred set of temporal and space directions, those corresponding to the relativistic inertial frames. Okay, they are related by the Lorentz transformations. But the main point stays the same as in Newtonian gravity. Space-time is a continuum, is a background structure over which all the other dynamical physical entities live and interact, is not influenced by all the other dynamical physical entities. Okay, from this point of view, it's very similar. In relativity, this changes. So whatever I'm going to say about gravity is based on some main lessons about general relativity, not because I have any religious respect for a particular theory, but because it's the one that seems to work fine up to now. So we try to see what we have to learn from that, and then we move on. So general relativity works well, so it's better that we try to see what it teaches us. And it is used, I mean, it works extremely well. As far as gravitational physics and space-time properties are concerned, general relativity is successfully applied as a classical theory in conjunction with quantum field theory to describe everything. everything we have current access on, from astrophysics to cosmology to particle physics. You could say that particle physics is quantum fields on a special solution of relativity being flat space. But the framework is the same. Now, what do we learn in relativity? We learn that speaking about gravity is the same as speaking about geometric properties of space-time. We retain the continuum picture of space-time from special relativity and Newtonian gravity. But what is special is that space-time itself becomes a physical system in the sense that not only is characterized by quantities you can compute, like the geometric properties, but it does interact with all the other physical systems. It changes its configuration depending on the configurations of all the other physical systems, and vice versa. It's a physical system on its own, with its own independent degrees of freedom, dynamical degrees of freedom, but on par with the other physical systems. This is huge. If you haven't realized how huge it is, it means you haven't thought about it. It's a bit like with quantum mechanics, but I'm sure that you have thought about that. If you're not shocked and you're not really puzzled by what the theory seems to be telling you, it means you haven't thought about it. So depending on what the mass energy of physical entities, physical fields and particles and systems is, the local geometric properties of space-time are modified. Vice versa, depending on what the geometric properties of space-time are, matter behaves in a different way. Yes?
Is it not possible to reduce space-time to one foliation?
No.
No? But isn't that but we can say it's
One fixed foliation? No. You can foliate many space-times, not all of them admit a foliation, but you can admit a foliation. But what is a constitutive part of the theory is that nothing depends on the specific foliation you use for describing physics. Even on a space-time that is foliable, which again is not the most general case.
What I mean is deterministic, right? The theory is deterministic.
I'm not saying anything about deterministic or probabilistic. That's just the fact. It's deterministic theory to a large extent, in the sense that in the same sense that is part of classical mechanics and knowing initial states. If your space-time is foliable or global hyperbolic, then knowing initial states should allow you to determine future configurations of the gravitational field and other entities. There are some subtleties, but that's normally the case. But again, one thing is a space-time to be foliable and you to find that useful. Another is that the foliation you use is somehow preferred and is absolute or anything. That is not the case. Okay, let's look a little bit more in detail. General relativity is based on a way of modeling space-time when you have a topological manifold, a set of points with all sorts of neighboring relations, a differentiable structure, and then you have a continuum set of fields, or a set of continuum fields, including the metric, which is the thing that allows you to compute geometric properties, volumes, distances, spatial or temporal, angles, curvature, any geometric property you want to compute is a function of your metric field, which is your dynamical field encoding gravitational properties. Then you have all the other fields, scalar fields, vector fields, fermion fields, whatever else. Now, we will discuss later, it has been mentioned already a number of times in discussing reference frames and so on, that you also have a symmetry, although this is the basic setup, but there is a symmetry of the theory, which is a gauge symmetry, which is diffeomorphism symmetry, which somehow questions the physical essence of each of these ingredients, in particular whether the notion of manifold points or directions on the manifolds or paths on the manifold is per se of physical meaning. I will discuss that later, but still, you are in this type of formal mathematical context as a model of the world. In any case, in general relativity, like in Newtonian physics and special relativity, the world is described in terms of continuum entities, fields, and manifold and metric. Okay, each and all of these ingredients will have to be questioned when you try to go beyond classical general relativity. Which one you try to keep for whatever reason is up for discussion. And I will show you later on examples of results from the quantum gravity research in which several, in fact all of these, are in one way or another questioned. Okay, this is a picture of space-time, rather smooth. Okay, what is the problem? Given this is what we know about space-time and gravitational physics, what is the problem? There are many. There are many ways also to see what the problem is. Let me start just from the conceptual point of view. If you make a list of the main ingredients and lessons of general relativity on one side, and the main ingredients and lessons of quantum theory, quantum field theory, if you want to play the fancy guy, you make a list, they are in direct contradiction with one another. Which means that as a theoretical physicist, you are forced by the state of things to be rather schizophrenic. Depending on the type of problem you're dealing with, the type of energy regime or context, physical context, you either believe and trust a bunch of principles or another bunch. That's a bit of annoying. You can live with that, and we are living with that, but it's a bit of an annoyance. By the way, of course, it's not just a conceptual thing, because most physicists are not that conceptually picky. They would be very much willing to just use different concepts from the morning to the afternoon. But these differences from the conceptual level percolate to a different type of mathematics you use, different physical principles you rely on, and then different consequences at the physical level. So it's not just a conceptual thing. The moment you realize that, and you realize that already in classical GR, that any statement about gravity, from the stupid one, like the apple is falling from the tree to the ground, is secretly a statement about properties of space and time, you realize that the moment you change your model, your theory, your understanding of gravity, which is obviously from the name what a theory of quantum gravity tries to do, you are secretly or more explicitly questioning and trying to change our very understanding of space and time. And space and time, there's a longer story behind that, are the real scaffolding, the infrastructure out of which we build any model, any understanding of the world. So, well, I'm trying to argue slowly and from different corners that we are getting as foundational as it gets. Okay, let's be a little bit more formal. You can try, I mean, I told you we've been schizophrenic up to now, but we try to work with equations that apply to the world, right? And keeping somehow this double framework, you know, classical GR, quantum field theory. One way in which we do that, very widespread and very much useful and applied, is semi-classical gravity. So you have quantum fields, you extract numbers from operators and states, and one obvious way is you take expectation values, and then you place that as if it was a classical source for gravitational interactions and you know, part of the gravity plus matter system. Now, this works in the sense that you can do some physics, and a lot of what we do in cosmology, astrophysics, and so on is in this type of language. But we know it cannot be a more fundamental theory. There are many ways to do that. I'm not going through all of them, but I mean, on the right-hand side, the energy momentum tensor as an operator is in fact a function of the metric. That means that in fact this way of writing the Einstein's equation is a little bit misleading, because it brings you the idea that there is a source independent of your field that sources changes in the field, in the gravitational field on the left-hand side. But it's not what it is. You should put everything on the left-hand side, and then you're just constraining the conceptually simultaneous configurations of matter and gravity. Okay, it's not a source and something else. It's a global constraint on what the configuration can be. Anyway, you can pretend that's not the case. Then you compute the energy momentum tensor with a given metric. Then you put it on the right-hand side. That will change the metric, because now we have to solve the equations with the source. Then you take that new metric that solves the equations. You compute the energy momentum tensor on the right-hand side. That gives you a different expectation value. Then you put it back in the equations, and you compute a new metric with the new energy momentum tensor on the right-hand side. This process doesn't converge, even in the case in which we can actually follow it. So this is one way to see that this is not really a consistent, fully consistent story. There are many others. I'm not going to list all of them. One practical reason for not staying content with this sort of schizophrenic attitude in which some part of the world is entirely classical and the rest is fully quantum, and you try to combine them. People have put forward a number of arguments for why you need to quantize the gravitational field, so for why this type of setting is not viable, like Gedanken experiments. They're a bit of the type that were discussed in earlier lectures, in which you say, well, if I have a quantum object, that quantum object will go in a superposition. If there is a superposition of that object, there will be a superposition of the space-time or gravitational field that is sourced by that. And therefore, I cannot stay content with the classical description of the gravitational field alone. Anyway, they are a little bit in that spirit. None of these arguments is a proof of anything. And there have been counter-arguments, but together they build a picture that makes us unsatisfactory with the status. Okay, so there are, of course, just physical issues. There are situations which we know, although we don't have direct observational access to them, we know are there, out there in the universe, that resist any description in terms of semi-classical gravity, or let alone classical gravity. And the singularities at the center of black holes and the singularity at the beginning of the universe, the Big Bang. In general, any situation in which the gravitational field is extremely strong and the quantum fields are in states corresponding to very high energies or start probing very small distances, are most likely requiring a quantum treatment of the gravitational field and of space-time itself. There are many models in cosmology. I leave to the theoretical cosmologists to debate which one is the most successful. Each of them, you can argue when you look at the details, either rely on assumptions about a regime of physics where you would rather need a theory of quantum gravity, or make direct assumptions about what a future theory of quantum gravity will have to confirm. In inflation, the very nature of the inflaton and the energy scale of the inflaton at the beginning of the universe could actually be dangerously close to the Planck scale. In bouncing cosmologies, the very physics of the bounce that replaces the Big Bang singularity is unclear in classical gravity, and so on. So these are contexts in which semi-classical gravity or our effective field theories call for a completion from a more fundamental theory. Then there are a number of things that are not normally tied to quantum gravity, not except the last one. But when you think about it, it's possible that quantum gravity will at least complete the story, if not solve the issues Dark matter is a bit ambiguous. I don't know if you know what the problem of dark matter is. It's just that galaxies don't rotate as it seems they should, given the matter content that we see in the galaxy. It's a phenomenon at sort of intermediate scales from the small to the very large ones. So it's unclear why quantum gravity would have to do it, but there have been proposals for the missing matter content being given, for example, by super small black holes, which would be produced by quantum gravity effects, and there are many other proposals. Dark energy is an extremely large-scale phenomenon. It has to do with the large-scale acceleration of the expansion of the universe that we see. But again, I will discuss later on how quantum gravity could have to say with that. Black holes is even more clear. You must have heard about the information loss paradox. I mean, the physics of black holes shows, at least on the theory level, that something with the semi-classical picture of space-time coupled to quantum fields is probably wrong. One of the basic assumptions. It could be unitarity, it could be locality, it could be the equivalence principle, it could be something else, but something must be wrong. And there is another way to pose the issue with black holes. We know for theoretical consistency that black holes have a entropy, but a black hole is just a region of space, although causally peculiar, which means that a region of space has entropy. Now, if a region of space has entropy and you interpret that entropy in the Boltzmann sense, you're counting microstates. So you're basically saying that there are microstates in a region of space that are not just captured by the given macroscopic configuration of geometry. So this again points to a quantum gravity description of these microstates, these microscopic degrees of freedom. I mean, this is just survey of motivations. I'm not proven anything. Okay, so how you approach each of these issues depends on the specific perspective you take. So now I will start discussing a bunch of possible perspectives. Yes?
Yeah, so with things like space-time thermodynamics or like black hole thermodynamics, the entropy we have is a purely classical result. It's another charge of diffeomorphisms, and we don't need to assign a statistical interpretation to it. And also, sometimes we can't even do that.
In which case you can't? Which results are you referring to?
What it is, for example, in like strongly coupled fields, there's like what you said, like what you showed is, on previous slide, when you have like Shoshan and Jitters are equal this, and if the coupling is strong enough, there's, for example, like no clear separation between a gravitational field and the matter fields. So then the statistical interpretation is ill-defined.
True. It's also true that in that kind of context in which there's no separation between the two tight positive degrees of freedom would be another instance in which the very description given by semi-classical gravity would fail. Okay, so there's no real way out. There's something missing there. I agree that, as I said, none of these arguments is a proof of anything. You can question the statistical interpretation of the entropy. I wouldn't say you can just be content with stating is a charge of diffuse because
this is true. This is a theorem.
Yeah. I'm not saying you cannot be content with that, because you will have to explain what that diffuse symmetry come from and what sort of degrees of freedom you're really addressing with that. Because there's an issue with gauge symmetries and the true degrees of freedom of gravity when you're out of the perturbative description of linearized gravity. So I agree. I mean, there is also, I didn't mention it, but you can also try to explain that entropy from entanglement across the horizon and entanglement of matter fields across the horizon. So you don't have to call for microstructure of the space-time. But even in that case, when you compute that entanglement entropy, it diverges. In order to make it a sensible description of thermodynamics, you have to put a cutoff. That cutoff is nowhere motivated from the field theory point of view, would have to be motivated by some completion of field plus gravity framework. In fact, it's normally at the Planck scale. So again, you can approach the issue of black hole thermodynamics or space-time thermodynamics in many different ways. From each one of them, you you find hints that you have to go beyond the framework of semi-classical gravity. No proof of anything again. But okay, let me, before we jump into the dark, let's clarify one other point. Can we avoid, or at least postpone, foundational issues about the deep meaning or nature of space and time? Humans, and physicists in particular, are a lazy bunch, so of course they tried. So what is the way in which you can try to do quantum gravity without tackling any of the foundational issues? You stay at the perturbative level, and then you just complete formally the theory, but all the basic principles are those that you can use in a perturbative setting. What is a perturbative setting? We take classical GR, you expand around a particular space-time background, normally flat space, because this approach is favored by particle physicists. So you start from flat space, you add perturbations, which are basically gravitational waves, and you quantize those perturbations. You have a quantum field theory of a tensor field that gives rise to the notion of a graviton, a particle mediating gravitational interaction, which is intrinsically a perturbative concept. And then you try to complete a non-perturbative level, and there are arguments that say that the non-perturbative completion of linearized gravity has to be full GR. So if you were able to quantize the linear theory and then look for a non-perturbative completion, making it sort of consistent, you have under control a definition of the quantum theory, avoiding big foundational issues. Why? Because you can define causal structure, space-time properties based on the background. You can rely on that, even if they fluctuate. But one thing is to have small fluctuations around the clear notion of time, space, causality, and so on. Another is to really have an entirely different understanding of what all those notions mean. So you can proceed. You can quantize by standard QFT methods in flat space. It doesn't work. So you can prove that there are indeed two helicities. These are the two graviton degrees of freedom per point. It's a field theory. But it doesn't work because as a quantum field theory is not consistent, it's not perturbatively renormalizable. What does it mean? It means that any order in perturbation theory, there are new divergences that you cannot reabsorb into a finite number of renormalizations or couplings. So it's not a consistent quantum field theory already at the perturbative level, even before you try to complete it somehow. So what is the lesson from this? That if you're looking for a quantum gravity vacuum, that is not the Fock vacuum of gravitons. That the UV complete theory, whatever it is doesn't have a Gaussian fixed point. It's not a free theory, even if you want to keep the field theory description. And the fundamental degrees of freedom are not gravitons. Okay, this may sound trivial, but according to a number of referee reports, it's not. Okay, this doesn't mean that this type of framework is not important. In fact, any more fundamental theory will have to recover it at the level of effective field theory, because to some extent it works. Just like the theory of phonons quantized around a given fluid works and helps you to do things. A description like this, we use it. I mean, gravitational waves are amazing. So if there are small fluctuations due to the quantization of those degrees of freedom, good, we can learn things. But it's not the definition of the theory. We have to reconstruct all the ingredients of this effective field theory from a more fundamental perspective. And when I say all the ingredients, I mean including flat space. From a more fundamental perspective, flat space is not a vacuum. Flat space is a highly excited special state built out of something else. Okay. So, okay, this simple, this, let's say, more straightforward, non-conceptually puzzling route doesn't work. At least this cannot be the story. What are other routes that people have followed? So there are two main things you can do in reaction to the failure of perturbative quantum gravity. Okay, perturbative quantum gravity fails, we have to quantize non-perturbatively. It means that you can try to stay conservative and say, okay, we have a classical theory, let's apply some other quantization algorithm that doesn't assume any split into a background and plus perturbations, and see how far we can go. But we maintain continuum fields, including the metric, as the basic degrees of freedom. Or you can say, let's extend the framework to include more degrees of freedom or other symmetries so that the perturbative quantization is well consistent, and then we also look for a non-perturbative completion. These are two logical paths, okay? And now I'm going to say a bit about both. A caveat, very often you hear that the problem of quantum gravity is the problem of unifying classical and classical gravity and quantum fields, or even stronger, unifying all the forces, all the interactions. I just want to clarify. If by unification you mean that you're looking for a unified conceptual mathematical framework, sure, no doubt. A theory of quantum gravity, however you try to define it more properly, has to treat in a common framework gravitational physics and quantum field theory as we know it, or obtain both from in some corners, in some approximation, but indeed you're looking for a single framework. If you mean that you're looking for some new substance, some new entity, a field, or something else, so it's a single one that in different approximations behave like gravity or matter, that's also possible. If it happens, great. If you have a candidate, please tell me. And it's fine, many approaches try to do that, but it's conceptually a different thing, okay? The first thing is almost a necessity by the definition of the problem. The second one is not. It will characterize maybe as a plus, as a big plus, specific framework, specific proposals, okay? Don't mix the two things. Okay. Quantum gravity has about 100 years, if you trace it back to the very, very first attempts. So what do you try to do? In the first strategy, as I said, you take GR and you try to quantize it. You try to employ standard quantization techniques for gauge theories, because you know that classically gravity has a gauge symmetry, and you try to go as much as possible. So perturbative quantization, we mentioned it. Canonical quantization is another main one. Covariant path integral quantization would be another one. And well, this started in the 60s with DeWitt, Wheeler, and so on, and it never died because we are advanced enough to keep ideas alive. Okay. What does it mean to canonically quantize GR? To give you a flavor, again, it's not a full lecture. It would take a couple of hours just to develop the formalism. Well, what do we do when we canonically quantize a field theory? We foliate space-time in terms of some foliation vector. If you want to be formal, you just split space and time, choosing some particular time direction. Then you identify the phase space of variables of your classical field theory. In the case of gravity, you end up with the special tree metric, the metric defining the intrinsic geometry of your slice, of your space, and the extrinsic curvature, which basically tells you how the slice embeds in the four-dimensional space-time, in the four-dimensional manifold. This is a bit like position and momentum. Just like for a particle, the position tells you where you are in space, and the momentum tells you how you embed in space-time, how you move. The same is for geometry, intrinsic tree metric and extrinsic curvature. But this is okay. Okay, you're dealing with geometry as a dynamical field, but that's what you already learned to do in classical GR, so it's all good. The peculiar aspect comes when you ask what is the dynamics, what is the Hamiltonian that evolves phase space variables. It turns out that the theory is a totally constrained system. Diffeomorphism invariance implies that the total Hamiltonian, what you derive formally as the Hamiltonian of the system, is in fact a sum of constraints. The constraints enforce, in fact, diffeomorphism invariance, or in more physical terms, they tell you, once you impose them, that the foliation you've chosen is entirely arbitrary, is entirely unphysical. It doesn't change anything you compute and try to measure at some point. So there is the one that basically imposes that spatial diffeomorphisms are a symmetry, so don't change the physics. And the other one, the scalar constraint, tells you that the particular temporal direction you've chosen is immaterial, has to be immaterial. So on phase space configurations that satisfy these constraints, you see no evolution with respect to a temporal direction and no localization on the manifold because of the constraints. What does it mean when you go to at the quantum level? Again, all this is rather formal, otherwise we would have a theory of quantum gravity. But what would be the scheme? You have functions on phase space, you quantize, they become operator that you have to represent on some Hilbert space. You have a wave function or quantum states that are the elements of your Hilbert space. Formally, you can proceed, very formally. So you have a wave function that is going to be a function depending on the polarization you've chosen, either of your configuration variables or of your momentum variables. So in this particular case, functions of the tree metric, the probability distribution, if you want, of the possible tree geometry you have on space. But then, instead of satisfying a Schrödinger equation, it satisfies this constraint equation, which is called the Wheeler-DeWitt, the Wheeler-DeWitt equation. So the statement is not that your wave function evolves in time with a nice time derivative with respect to some Hamiltonian operator, but the statement is this wave function, in order to be physical, has to annihilate a certain operator version of the classical constraint. Okay. This is what people call the problem of time. And it follows from the classical theory. It's not a peculiar feature of the quantum, of the quantization of the theory. It's the statement that there cannot be time evolution if by that you mean evolution with respect to a particular temporal direction on the manifold. And that's the result of having diffeomorphism invariance. No temporal direction on the manifold has any physical meaning, per se. Okay, anyway, this the whole construction can be brought forward, but remains very formal. In particular, there's no definition of the measure of the scalar product to define the physical Hilbert space, the space of solutions of the Hamiltonian constraint equations. But in fact, even before, you have a function of a function on the manifold. So it's a functional. If you try even at the kinematical level to compute a scalar product between wave functions, you have to have an integral over three metrics, right? Just like for a particle, you have a scalar product between two wave functions, functions of the position, you have to integrate over space, over all possible values of the position. So if you knew how to integrate over tensor fields, you would have solved, for example, the problem of writing down the measure in a path integral in scalar field theory, which requires that you integrate over functions of the manifold, the scalar fields, right? So that's a difficult problem in functional analysis. Okay, so the formalism can be written down. You learn a lot conceptually, and you can use it. In fact, it is used in semi-classical approximations for a number of simplified cases, but is not the definition of the theory. Yes? Say it again, sorry. If you can't foliate the space, you can't do this canonical quantization, or? Is not? If there's no foliation? There's no preferred foliation. So, because you said not all space-times can be foliated. It's true. You're right. I should have said at the beginning, the whole canonical procedure can be started only if your manifold is topologically global hyperbolic. If you start having holes, for example, you just cannot proceed with canonical quantization.
So if you had singularities, let's say, in your space-time, you wouldn't be able to do this program?
You cannot apply canonical procedures. You have to quantize the geometry by some other method. For example, the one in the next slide.
Okay. So then I guess in some well-known space-times, then you can't proceed with this, or how do they deal with that?
Okay, I would say, and I'm not alone, that for example, even a black hole space-time is not followable because of the singularity and so on. There is a little bit of debate whether in the argument you bring in singular space-times or not. But otherwise, as I said, any manifold with a hole will not qualify for a viable topological manifold for canonical procedures. A bit more general, but similarly formal, is the idea of quantizing covariantly by sum over histories, by a path integral method. For simple systems, we know that the two procedures are equivalent, but gravity is not a simple system, so we don't have that type of equivalence ensured by anything. It's a bit of work to prove in which case you can have at least formal equivalence. But what is the idea? Well, your histories are the space-time geometries, the four-dimensional metrics in 3+1 dimensions. So you try to define a transition. Again, here I'm in the global hyperbolic case for simplicity. You have some initial boundary data, some final boundary data, and the data could be the three-metric on the initial boundary and the final boundary, like initial position and final position for a particle. In between, you can put all sorts of, if you don't impose the equations of motion, you can put in the bulk all sorts of four geometries. And you know that in the quantum theory, you don't work with solutions of classical equations of motion only. You put any sort of wild history in between initial and final states. And you have to write down a sum over all possible four geometries. And again, of course, here it's all formal. Why? Because again, you should be able to define this functional measure. Is a sort of upgraded difficulty from scalar field theory path integrals. If you want a straightforward semi-classical approximation, well, this is a sort of local measure of non-exponential type, and here you have the exponential of the Einstein-Hilbert action for classical GR, so that in a straightforward saddle point type approximation, you have the equations of motion. This is like why in a path integral you have that exponential, because you want to take h bar towards 0 and find classical gravity as a dominant set of configurations. Anyway, that's the idea. And again, a lot of work in trying to make sense of it and applying it in semi-classical approximation, in simplified context. But again, we don't really know how to fully define the theory. This, again, started in the 60s from the same people, De Witt, Wheeler, and so on, but then also Hawking, Gibbons, Hartle, and a bunch of others. In the same sort of spirit, take classical GR, quantize, we have modern versions of these early attempts. Because if you throw an idea in a room full of clever people, they will find progress. They will find ways to extract something good out of it. And so many or several of the modern quantum gravity approaches are a sort of a success story built on these shaky foundations. Let me mention one that is a little oldest tradition. How do you know we managed to give meaning to path integrals for gauge theories or even for a scalar field theory? You go on a lattice. You discretize. That solves issues with the functional measure, because then you have a finite number of space-time points where your field has to be defined, takes values. And then the path integral per se on a lattice is well defined. It doesn't pose too many mathematical difficulties, and the real task becomes to take thermodynamic and continuum limits. Like in any, I don't know, even condensed matter. You first have all your cutoffs, so then you say, I want to see what happens in a thermodynamic limit, and you have different phases and phase transitions and so on. So people did the same for gravity. So you take classical Einstein-Hilbert action, you find a way to discretize it on a lattice. This may not look like, but this is the discrete counterpart in 4 dimensions of the Einstein-Hilbert action. Instead of the Ricci curvature, the Ricci scalar, you have what is called the deficit angle. If you take a bunch of, let's take a look at the 2-dimensional case. If you take flat triangles and you glue them along shared edges, in flat space, and let's assume they are equilateral for simplicity now. If you are in flat space, you can only glue 6. Because an equilateral triangle will have a 60 degrees angle. You glue them along edges around a vertex, you can only fit 6. If they're equilateral and you fit more than 6, you have curvature. If you fit less than 6, you also have curvature, positive or negative in the 2 cases. So you see that you can have a definition of curvature which has to do with the angle, the deficit angle at the vertex in this 2D case is the difference between 2 pi and the actual number and the actual sum of of the internal angles of the triangles that you glued. This is the number here. So it's a measure it's a discrete measure of curvature. It's in fact a discrete definition of curvature. And this is the equivalent to the volume element of the metric in the discrete case. Is the area of the triangle from which, in 4D, in here would be just absent because it relates to the point, is a local volume measure. Anyway, the point is, you take classical GR, you discretize it in the most careful way on a lattice, and then you want to define the path integral. Notice that in defining the action and in trying to explain how you are discretizing the notion of curvature, I had to use 2 pieces of information. What are the edge lengths? So I said, in the equilateral case, then you do something. What is the value of all the edge lengths is part of the geometric information on a lattice. It's a distance, right? An edge length is a distance between 2 points, so obviously it is metric information. Another piece of information I had to give you is how many triangles I was gluing and how. So it's a combinatorial information. So on a lattice, there are 2 sets of data that encode geometry. The edge lengths and the very combinatorial structure of the lattice. So suppose you want to make geometry dynamical, you have 2 options, or any combination of them. You can say, okay, I fix the combinatorics. I stay with a given lattice, and I vary the edge lengths, and I sum over all possible assignments of edge lengths. This is the counterpart of summing over all geometries for a given lattice. You still with me? More vigorously? Make sounds? Try left, right? Okay. So one way in which people try to define path integrals for quantum gravity in the discrete context was choose a lattice, assign edge lengths, and sum over all possible assignments of edge lengths as a sum over geometries with the weight given by the exponential of the discrete version of the Einstein-Hilbert action that is called the Regge action. The other complementary way to do things is called dynamical triangulations. Takes the exact opposite perspective. Fix the edge lengths and you sum over all possible triangulations, all possible lattices for a given topology. Because that's the other set of information defining geometric data. But again, with the same sort of weight, exponential of the Regge action. Yep.
So it is quite intuitive how you would build from this like a discrete version of a Riemannian manifold. But you would eventually like to have a Lorentzian structure.
Yeah, this is also done for Lorentzian structures. You can define piecewise flat Lorentzian lattices.
Okay.
And it's a bit more involved.
Okay.
But it's exactly the same template. You just have to be a little bit more careful. You have to distinguish simply time-like and space-like edge lengths, and you have to define in a slightly more involved way the curvature, the measures of curvature, well, whatever, and the expression for the action. But everything is.
Could you alternatively just Vic rotate it and consider it linear?
Okay, that is subtle, because Vic rotating with respect to what? Vic rotation uses heavily in flat space the fact that you have a temporal direction that you Vic rotate, which is an absolute. Here you don't. So you can define Vic rotations, but it's a bit more subtle. And the point is that if you Vic rotate, you change the weight, but the set of configurations you sum over will be the same. And it's not obvious that that's what you want to do. Anyway, yeah, people do that, but it's a more subtle issue that you could imagine. So it doesn't really help per se.
Fair enough. Thank you.
Okay, lattice path integrals. Do I have another 5 minutes?
5 minutes, yes, that's all.
Yeah? Okay. So, loop quantum gravity that you may have heard of started, at least, now it's very diversified, but it started as the straightforward canonical quantization of classical GR, like I discussed earlier in terms of the trimetric and the extrinsic curvature, but performed after you change variables in the classical theory and you put the classical theory in a form that is much closer to gauge theories in terms of a gravitational connection and the tetrad as the independent variables, more or less conjugate to each other. This seems, at the classical level, it doesn't change anything, but it allows you to employ for the quantization a number of techniques from gauge theories, and it allowed all the initial progress. In particular, it allowed to define in full rigor, even too much to my taste, what is the kinematical, at least, Hilbert space of the theory, with a number of choices, of course, that we can discuss and are discussed in the literature. But you know what is the kinematical Hilbert space of states of quantum space at the non-perturbative level. It's a rather impressive achievement if you come from the older story. I say kinematical because then on these states, as we have seen, you have to impose the dynamics, meaning the Hamiltonian constraint, in order to have physical states. And this is challenging for a number of reasons. But I want to emphasize a first lesson from this kinematical construction. Apart from the procedure and the mathematical beauty or not of it, the end point is that you end up with a Hilbert space of states which are fully characterized, at least a complete basis of them is fully characterized in purely combinatorial and algebraic terms. A typical state is a linear superposition of stuff like that. Graphs labeled by representations of SU2 in the specific case, or if you want the Lorentz group. So algebraic data from the representation theory of SU2 and combinatorial data from graph theory. That is a particular example of a quantum state of space itself, from which you are supposed to reconstruct all geometric properties and some appropriate limit continuum physics. Of course, a generic state is a linear superposition over both the combinatorial data and the algebraic data of that type of states. What I want to emphasize here is that this is the result of not trying to do anything fancy in quantum gravity. Take the classical theory, writing as a gauge theory, you know you can, mathematical is under control, quantize using the most boring quantization algorithm you can think of, canonical quantization, do a number of forcefully fancy things in between because it's not easy to actually proceed. You have to make some choices, but at the end of the day, you arrive at a picture of quantum space which is vastly different from the conservative perspective you started from. You don't have a metric anymore. You don't see a smooth manifold. You see combinatorics and algebra. So another point, again, without doing anything fancy, you can take functions of the metric, or more generally, function of phase space variables, which are your observables in the classical theory, you quantize, they become operators. In particular, geometric operators. The area of this table is a function of the metric of the world in a particular region. It becomes an operator, an observable in the theory. There are some caveats, and you quantize it, and you check what the spectrum of that. It turns out that basically every geometric observable people have been able to compute the spectrum of as a discrete spectrum, which again is one of those things that if you don't think about it, you say, well, so what? Quantum mechanics, many things have a discrete spectrum. Then you realize that you're talking about geometry. It means that there is a minimal gap between possible geometric values of the area of a table. It looks smooth, but effectively it's not at the more fundamental level, and the volume of the room, and so on. Again, the whole continuum picture of fields and so on vanishes. Then you have to impose the Hamiltonian constraint, and there are many different constructions. It's very hard, but again, the main point is that what the Hamiltonian constraint will do is act as an operator on this type of combinatorial algebraic states and give you some superposition of other states of the same nature with a different combinatorial structure, different assignment of labels with some weights. That's evolution of space in this context. And obviously it doesn't resemble the equations of motion or GR in terms of a smooth metric with derivatives and all of that. But that's what comes out of the quantization in a conservative approach. You try to be boring and the world doesn't allow you. Okay, if you can look at in this context at the counterpart, the covariant path integral counterpart of the theory. If you have states which are combinatorial and algebraic, the histories will be combinatorial and algebraic, and will be such that if you take a typical history and you try to cut it and slice it, you find the same type of combinatorial algebraic states. A typical history in this context is called the spin foam, while the states were spin networks. But again, it's some cellular complex labeled by algebraic data. And in a definition of the covariant dynamics, you have to sum over all possible cellular complexes labeled by all possible, allowed by whatever model you're dealing with, algebraic data. This is what replaces the idea of integrating over smooth geometries or four-dimensional geometries with the Einstein-Hilbert action as a weight. And the challenge becomes to try to recover this sort of picture in some approximation. Yes?
How would you assign the various models different spin values, spins, right?
Well, I didn't tell you how you define the models and how you define the dynamics. I just gave you the basic ingredients. And to some extent, you can derive them from the classical starting point with choices that you have to make. But then we are entering the debate about model building, what sort of specific construction you build. Here I'm just illustrating the general elements of all the models around. And I'm already over time. Okay, if that didn't sound fancy enough, I want to close with this so that tomorrow I have exhausted the part, at least, of the overview of current formalisms and approaches. Okay. I would have been happy to give 3 hours of lecture just on this because I work mostly on this, but I just want to give you an idea. So if the old story before was not crazy enough, this is crazier. So a lattice, take a special lattice, can be built out of cubes that you glue together to form a cubic lattice, or if you want to be a little bit more fundamental, simplices, or little pyramids, tetrahedra. Why? Because any cube you can split it in tetrahedra, but not vice versa. So you take a simplicial lattice and you glue simplices together to form a 3-dimensional lattice, and then you can ask what is the evolution of that, or a 4-dimensional extension of that. okay? But the building blocks will be these simplices. You can write down a field theory, not over any space-time, but over some more abstract algebraic manifold, whose quanta are those simplices. So the space-time is like a quantum many-body system of those simplices, and in the Hilbert space of states, you find those that are glued together to form lattices as a special case. But in general, you have a dynamical theory of simplices, these building blocks that interact, are glued to one another and in all possible processes, and that defines your discrete and algebraic space and space-time. So the same type of structures you had before, generated by a field theory. And in fact, you can be more specific. You write down formally the partition function of the theory. You expand it in Feynman diagrams. You've done quantum field theory, right? The Feynman diagrams of a scalar field. In this case, you construct the theory so that the Feynman diagrams look like four-dimensional lattices, which are the possible interaction processes of these building blocks. And you construct models so that when you write down the amplitudes, the Feynman amplitudes for each lattice, they look exactly like the spin form models that you could derive independently, or the discrete gravity path integrals that you could motivate independently. So you bring them together within a given framework. And the only thing I want to emphasize here is that the type of fundamental degrees of freedom are those combinatorial algebraic data. Again, you lose even more track of classical continuum GR and other gravitational theories. And the fundamental definition of space-time physics is in some abstract field theory of these algebraic combinatorial building blocks. So you are now already moving in the direction of a third route towards quantum gravity that I will discuss tomorrow, which is that of emergent space-time, not following from canonically or covariantly or otherwise quantizing classical GR and classical space-time. Anyway, I close it here and I will keep going tomorrow after saying that this is only a few examples of the formalism and approaches that people are following. So there is other stuff that I'm not going to discuss. Okay, so yeah, see you tomorrow.